Two Kirchhoff's laws apply to electric circuit calculations. These laws are based on energy and charge conservation laws. Gustav Robert Kirchhoff, an outstanding physical scientist of the 19th century, formulated these laws. Let me expand on the first Kirchhoff's law and its application. This law is based on electric current continuity and applies to electric circuit nodes as follows. An algebraic sum of currents within a node equals 0. That is, an electric circuit node is a connection point of 3 ohms and more. We assume positive current if it flows into the node and negative current if it flows out. For instance, if there is a T-shaped electrical circuit node where electric currents flow through 2 wires, current will flow from this node through the third wire and it will equal to the product of 2 incoming currents. Let us demonstrate the Kirchhoff's law in this circuit, where 2 resistances are connected to a power source. Let us measure the current from the source. It is 31.6 milliampere. Now let us measure the current of each resistance. The first resistance corresponds to 3 milliamperes, while the second corresponds to 28.6 milliamperes. Total gives exactly 31.6 milliamperes. This law has simple physical implications. If it did not work, the whole node would continuously accumulate an electric charge. However, this does not happen. There is one more definition of the first Kirchhoff's law. In any node, a product of inflowing currents equals to a product of outflowing currents. It is obvious that 2 definitions are equivalent, and you may write equations at your discretion. Only agreed current plus-minus signs matter. That is, we can't use different signs of inflowing, outflowing current for different nodes when we describe a certain electrical circuit. Generally, we select current directions in electric circuit arms randomly to make equations based on the first Kirchhoff's law. Currents of different directions may even be absent in all the circuit nodes. We may come across that all the currents flowing in arms joining in a node flow to or out this node, violating the principle of continuity. In this case, one or more current flows will be negative. This proves that the flow in the opposite direction